So welcome to the Around Sound talk. I think I'm second this year, so you might not have a huge idea of what to expect. And actually, every time it's a bit different. Frequently, we will have people from industry, or one of us showing things that are, our special passion or something we do otherwise. And I was thinking along these lines. I was actually intending to first do a talk on subharmonic distortion, as it's one of my favorite topics and I have some invention in that domain. And then I thought, well, actually, Al asked me, why don't you do what you did last year? He really loved the last year's talk, which was chaos in sound synthesis. In other words, fuzz pedals and mixers in feedback and what these things can do. And they can do quite a lot of interesting intermittent stuff, kind of unexpected sound design or indeed performance. But then on Monday, doing a lecture on acoustics, I realized, bloody hell, we don't really have a good lecture on spectral analysis anymore. In fact, even back in the day when I used to teach the signal processing with APDI, it just didn't fit in there. And it was just that advanced as well, such that it kind of scared people off more than anything. So I'm taking now the opportunity to deliver this lecture, and I mean, it's supposed to make you fall in love with signal processing, really. It's actually one of the things that made me really fall in love with signal processing for audio, because there's some really genius things in there, also things that I don't know the details of, and I'll talk about that, but also some really, really kind of revealing facts of life and signal processing and audio. So yes, I have a slideshow to kind of back me up, which you don't see right now. And I have a pen or a marker that should allow me to draw a few things once I feel like it. But actually, I'm gonna try and make this a lovely little kind of free talk, and please feel free to interrupt, ask questions, and all the rest of that. So the topic is spectral analysis. So what is a spectrum? You guys feel active? You wanna make this a chat? Would you want to try and define what is spectrum?
Like a range.
A range, exactly, of what? Well, probably the most kind of entry-level term, which is typically useful, is vibration. Okay? So it's a range that relates to vibrations, right? And in fact, it relates to the speed, pace of vibrations. You see, I'm kind of omitting the word frequency for now. But I guess everyone knows what frequency is. Now, the thing is that frequency is a concept. That's why I'm also trying to avoid it at early stages before I thoroughly define what it actually means. The funny thing about frequency, and this will come through once we look at some detail as well, is that single frequency exists only if its duration is infinite. Okay? It's a really funny thing, but actually mathematically this is correct. So if I have a sine wave, right, I guess everyone is cool with sine waves having single frequencies. But if that sine wave lasts for a second, it's actually not a pure sine wave. If it lasts for a tenth of a second, it's even lesser of a pure sine wave. And if it lasts for a single digital sample duration, or I should say time interval, then what is it? Well, it's just a click, right? It's just an anomaly. It is one single sample left out of this sine wave that I've progressively shortened. And in the range of a few milliseconds, or probably less, this is very audible, right? As I shorten my sine wave, it becomes clickier, and I will progressively lose the sensation of a pitch altogether. Actually, if I have only a few periods of a sine wave, I will not identify the pitch that corresponds to its frequency. Maybe I should also be quite meticulous about these terms as well. So frequency is a term coming from physics, and it denotes the period duration. In fact, it denotes the inverse of the period duration. So only periodical signals have fixed frequencies, whereas pitch is a term that comes from psychoacoustics. Well, it comes from language, and then psychoacousticians said this is ours. But they're right about doing that, because pitch is something we declare about something we hear. And there is a huge amount of experiments that prove that we may be fooled, deceived, in terms of which frequency does the pitch correspond to that we hear. Right, so I'm trying to delineate these terms, but actually I'm focusing on frequency here, because as it stands in maths, it has to be infinite duration, because you see, as soon as it starts or stops, it is not truly periodic anymore. Okay? And we will see how this pans out in spectrum as well. Now, just to continue a little bit more with terminology, when people, even professionals, use the word frequency, they're actually most of the time inaccurate, not just because they're not talking about infinite sine waves, which exist only in math, but also because they're talking about spectral components, actually. Okay? So spectral component is that really beautiful key term that, you know, gets you a job at an interview for an audio-related whatever thing. Okay, so spectral components is really what we're looking at when we do spectral analysis. Now, taking things apart into spectral components is, I should say, product of monkey brain. Right, so it is not a part of reality. And in fact, the biggest issue I have with the paradigm around spectral analysis is the little riddle which goes, you can reproduce every sound using sine waves. Okay? Well, I can probably feed myself on black markers for 10 days without dying as well. It's not the question whether I can do it, the question is whether it makes sense. Okay, it doesn't make sense to try and survive 10 days on eating black markers from the store we have. We have a box full of black markers, you can imagine. So the question is whether it makes sense. And in certain cases, it does make sense. In fact, spectral analysis that builds on sine waves, okay, this is important, it's just one of the types of spectral analysis that builds on sine waves. The one that does is called Fourier transform, and it stems from analysis, believe it or not, of heat waves in metals. It was a kind of an early physics thing. Does it say? I think my slide says it somewhere. 1700s? It doesn't say. Okay, but it's a few hundred years ago, putting it roughly, that it was apparently useful for heat waves in metal. Now, the reason why we're stuck with it is because at some point mathematicians devised a really neat optimized scheme. So FT stands for Fourier transform and FFT stands for fast Fourier transform. And this optimized algorithm is really fast. And it could be implemented in early computing machines as well. And that's kind of the main reason we are stuck with it. Now, the question arises, when is dissecting, or I should say, what's the good term here? What are we doing with the sound? We are resolving, right? When is resolving a complex sound into sine waves meaningful? Any ideas? Well, it has to do with its similarity to something which is periodic. So, more terminology, periodic is something that has an exact repeating period duration. Quasi-periodic is something that almost does that, for lack of a more accurate definition. So actually, if we have quasi-periodic sounds, typically instrumental sounds that we identify to have a pitch, these quasi-periodic sounds can be very meaningfully analyzed by using sine waves. So when is it less meaningful, what do you think, to use sine waves to separate out spectral components? What's the opposite of sine, more or less, in audio? Excuse me? Sol wave is an exact periodic signal as well. Okay, so things that have pitch. So what are the sounds that don't have a pitch? Noise. That's a good one, right? So what happens with noise if you stick it into a sine-based spectral analyzer? What do you get?
Just the same value at every
Exactly, you get what we could call a flat spectrum, right? So every spectral region has the same amount of energy. Which means that what we've just done is we've taken a fairly simple physical phenomenon, most related to turbulence. Okay, every turbulent system is actually a noisy system, and depending how you drive it, you can get more or less flat spectral noise in a given range, bandwidth. So it's turbulence that can occur, but just by me doing that's turbulence, that's noise. So what I do if I take an analysis, a spectral analysis based on sine waves of some turbulent stuff I do, I'm using, well, depends on the resolution, but I'm probably using thousands of sine waves to describe that fairly silly turbulent occurrence. Okay? And it's in fact even simpler than that, because as soon as you have a resistor in an electronic circuit, it will give you fairly flat noise, spectrally flat noise. So just a resistor in a circuit does it already, and what I'm saying is, well, I'll just describe this using few thousand sine waves. So you see that there is something funny about this. There is another type of signal as well, which also has a flat spectrum, and that signal is the impulse. Okay, an impulse is your shortest duration of acoustic energy. And we can talk about these limits and the Dirac and all the rest, but it doesn't really take us much deeper, I would think, than actually realizing that if I plug a cable into a guitar amp, just as someone comes in with the guitar, that's great. You have an amp as well on you? No? So if I plug, I was just talking about guitar amps as you open the door. So if you plug in the cable into a guitar amp, you get an impulse, right? The speaker cone will jump out and back very rapidly. And the thing that you can relate to probably is that the sound of this impulse does have the bass, the mids, and the highs. So it's also a spectrally flat phenomenon, an impulse. Okay? So again, what I'm doing, if I dissect or dissolve, should have thought about a good term here and excluded all the bad terms. But if I do a spectral analysis based on sine waves, and I'm trying to describe an impulse, again, I'm using few thousand sine waves to describe something which is as simple as this or that or anything which is impulse-like. Okay, so I think this is fairly important because we do have machines which are sufficiently fast to not be stuck with fast Fourier transform. And the thing is that most processes that rely on fast Fourier transform, if the resolution is inadequate, if there's some anomalies, they will sound like a bunch of sine waves. It's how your bad old MP3 sounds. When there is a noise floor, you hear a lot of, you hear millions of sine waves going up and down, because that's how this type of signal is decoded. And the other thing that happens also is that your impulses just are not pure. Okay, if you want to really judge, one way of judging your reproduction system is pick an acoustic instrument that you really know the sound of and really make a staccato pluck on it, or whatever excitation mechanism, make a really short sound with it, and then listen to how this is being reproduced to the system. Because the transient sounds are the kind that we have evolved to appreciate quite a lot. Because you see, most of the auditory system, the evolution of it, was propagated by our survival, you know, coming down from the trees, whatever's still hanging around trees. So the promptness of it was crucial. The promptness of sound source recognition was crucial. In fact, our spatial ability relates to higher frequencies than the frequencies we hear. Okay, so the interaural time difference that I can perceive goes down to 10 microseconds, which corresponds to about 100 kilohertz. Well, about 200 kilohertz, right? So that's the funny thing about high sampling rates, that I don't hear a sine wave. I probably don't hear the one at 16K already, not. But my ability to hear the sound stage necessitates higher sampling rates. So you can play with this. If you have, you know, if you're recording an orchestra with a beautiful microphone pair, you do it 44, you do it 96, good chance that on a good reproduction system you will hear there is a difference in the amount of spatial detail. Because these very minute time differences, they're really important evolutionarily. They've developed to make us extremely alert to things, the direction from where they're coming. Okay, so that's a bit about sacking the whole FFT business. Why do we need to sack it? And how it's likely gonna get sacked sooner or later. And we already have probably about 50, maybe even 20 years that serious signal processing engineers have developed an analysis that suits audio much better, whereby they distinguish sinusoidal spectral components, they distinguish noisy spectral components from the impulse type components, and that's what you get as the result of the analysis. Okay, it is evidently much more complex algorithm. It can probably just about run real time, although I haven't seen a very good real time implementation. Last time I've played with it, it was in fact many years ago. It was a kind of a offline rendering command prompt tool called Loris, which was, you know, free engineers kind of, here you go, have fun. And I can tell you that, you know, stretching sound, for example, is hugely improved when you do it through this algorithm. And the reason is probably obvious, because how do you stretch an impulse? You don't. Okay, there is nothing to stretch about the impulse. How do you stretch a noise band? Well, you stretch it by resynthesizing the noise rather than taking the phase information and stretching it out in time, because the property of noise is that the phase information is so dense, and I'll talk about what phase information is. It's a bit of a early comment, really. But the phase is so dense that if you stretch it in time, it loses density and the audible quality of it changes. So you cannot really stretch noise very well without just resynthesizing a similar profile noise. And then the sine waves, well, actually the sine waves are also resynthesized by resynthesizing them rather than trying to stretch them. And you can achieve stretch factors up to 100, 200, 300, right? It's a command line tool. It can work overnight, things like that, like real stuff. And it all comes out really pure. It's just unbelievable quality. And that's one of the things which is an alternative, which is a great, probably the best alternative because it is inspired by the properties of our acoustical environment. Now, there are many more spectral analyses. One of them, which is worth mentioning, is probably wavelets. And I'll come to why that is good. It's essentially short sine waves. When I discuss FFT, we will come to why that is advantageous. But actually, you can separate out a complex signal into square waves as well. It doesn't have to be sine waves. You can take pretty much, I mean, that's maths, right? It's called the orthogonal transformation. The one that you take a complex signal, you dissect it, you derive multiple signals from that, such that when you recombine them, you get the exact same original signal. Okay, so in that sense, FFT is exact at the limit of resolution, maybe. But mathematically, it is exact. So there's no real issue with that. The issue is that the acoustic environment is not made up of sine waves. But there are a lot of impulses and a lot of turbulences, noise sources, and in fact, there's just a few quasi-periodic sound sources, like our voices and instruments. Would you think a fart is a quasi-periodic signal? I would argue that it is. Maybe it does not have a pitch. I mean, it really depends, right? But there is a definite fluttering, which is a kind of a sub-audible frequency, right? It maybe flutters like drops in the rate from 7 hertz to 3 hertz, something like this. Okay. Right, so I've kind of done this introduction just to, contextualize Fourier transform in 2023 and how some of us are really looking forward to never see it come back again. Nevertheless, it is probably one of the most miraculous things. As I started the lecture, it made me fall in love, one of the things that made me fall in love with it. In fact, I probably have to credit Peter Papon, who is the guy who taught DSP when I was at uni, and he made me fall in love with it in many ways as well. But in any case, let's dig into Fourier. Okay, so we know that it's suboptimal, it's not great, there's issues with it, but understanding it is really, really exciting, I would think. Okay, so sine wave, I kind of assume that you guys have a clue. But there is an interesting thing to consider, because a sine wave has a constant frequency, right? We figured that. But what is constant about a sine wave? That is the time signal. That is the sine wave. You see, it just goes up and down. And the funny thing about this time signal is that if this curve here is just a little bit flatter, but really just a tiny, tiny bit, such that you don't even see it being anomalous, if that is the case, it's already not a sine wave. And you will get harmonics appearing. It won't be a pure signal like that. So it is a really, really sensitive thing. In fact, in analog circuitry, it is near impossible to get a good sine wave because you just cannot exclude the nonlinearities. It's the way to create a sine wave, a good one, is digitally. So what is constant about it? I mean, the constant is the frequency when we hear it. I assume everyone understands that in order to hear this sine wave, it has to represent a time duration of how much? Well, 20 hertz, 500 milliseconds, 50. Less than 500 milliseconds, 50 milliseconds, okay? So it has to go up and down really quickly, and if the speaker does this trajectory really quickly, then we will hear a sound, a fixed frequency. But what about this is fixed? Well, the thing that will hopefully stick is the analogy to a bicycle. Okay, so if I'm riding a bike at a fixed speed, right, I have a fixed angular velocity, as we call it. And what happens is that if you look at me from the front or the back and look at me pedaling, you will see this motion. My foot, if you look at a single foot of mine while I'm pedaling on the bicycle from the front or the back, you will actually get a time signal. The height of my foot in relation to time will give you an exact sine wave if I'm pedaling at a fixed speed. So just to give you some grasp on, okay, what is fixed about this sine wave, what is fixed is angular frequency, actually. Okay? Cool. So the traditional thing in sound synthesis, blah, blah, is that you can create every signal from sine waves, whether it's meaningful, I've already discussed. The point being that the kind of signals that you encounter in studying sound synthesis, like square waves and sawtooth waves, can be constructed from sine waves. In fact, digitally, they always are. Okay, so I'm not sure I do want to go into band-limited oscillator topic right here. So let that be a catch, a phrase that takes you further. But in any case, the funny thing is that if you add up all those sine waves that you see on the left, whereby they are increasing in frequency, whereby they fit exactly in the period duration of the fundamental, and whereby they decrease in amplitude as you go higher in frequency. So that set of sine waves added, in other words, mixed together, will converge to an actual square wave. Okay? Which is cool, I guess. So that will allow us, if you turn it the other way around, to say that if we have a complex signal, and hopefully a quasi-periodic one, then what we will end up with is the set of sine waves that constitute this signal. And if it is a quasi-periodic signal, then all these sine waves are more or less harmonics of the fundamental, which means that their frequency is integer multiple of the fundamental. Okay, so I kind of guess you understand this already, but it was worth saying. And then we get what we call a spectrum. Okay, so vertically we plot the amplitude, horizontally we plot the frequency. And a single bar is the spectrum of a true sine wave, which exists only in monkey brains, because the sine waves around us are finite. And as soon as the sine wave is finite, it will get what engineers, I won't go into psychoanalysis right now, but engineers call it the skirt. And this straight line starts to have a bit of a skirt. So what happens is that the broad bandwidth is widening. And the funny thing is that as I'm shortening the sine wave, then the bandwidth is increasing. And if my sine wave is as short as a single sample, it becomes an impulse. And by that stage, the spectrum has totally opened up and become flat. So there is a continuum between an impulse and a sine wave, right? And the funny thing is that if you have an infinite signal in time, which is the sine wave, you get an infinitely narrow bar in spectrum. But if you have an infinitely narrow bar in time, which is the impulse, you get an infinitely broad spectrum. So there's a really funny back and forth there. And the funniest thing maybe is that if you have a Gaussian curve in time, you get a Gaussian curve in spectrum. And if you have a Gaussian curve in spectrum, you get a Gaussian curve in time. So there's a lot of beautiful stuff. I mean, if you like numbers, you're supposed to start really loving them in this context, because I always had a charm for numbers, but they just were useless, right? No one really showed me early enough what's the use of this thing. I mean, I realized that I can, count the change. Back in the day, when I was a kid, you were supposed to count the change. And I don't know. I mean, part of the reason why it was useful, because I could appear to be really clever, because I figured out ways to calculate quickly stuff in my head. And someone asks, what is 345 times 3? And I probably can't do it very quickly now, I won't bother. But I can spit it out. It's like, whoa, you're clever. And I'm like, sure. It's because I was horribly worried about being stupid, by the way. Most people, the way they develop, I've developed into, earning a living from appearing clever. The reason is that I'm horribly worried about being stupid. We normally develop in the opposite direction of what we actually fear. So I'm still probably quite fearful. Although at this stage, I really accept all the errors and the stupidities. They're quite charming. Okay, so we've seen a spectrum. Now, let's go on. I mean, the really interesting thing is yet to come. I will try to pay attention to your stamina, but I can probably go on for another, half an hour for sure, but maybe even a full hour. So let's see how this goes. Okay, the $1 million question is, how on earth is it that you have, this is the moment for my little drawing skill display. You see, the issue is I wasn't very fearful of not being able to draw as a child, so I never learned to. So this will be horrible. But the $1 million question is, how do I take such an arbitrary curve like this one, which in a digital domain, as you know, actually consists of fixed points and not much more, so just values in an array. How do I dissect this signal into its spectral components? What are the spectral components of this signal? So what you should be able to imagine is a set of sine waves that when you add them up, they produce the exact same signal. Ow. It's already challenging, and I would probably say, well, you can't really, can you? So what would be the imagined spectral component, the components of this signal? Well, the basic intuition that I hope you've kind of developed is that bass frequencies are slow and high frequencies are fast. So actually what I'm trying to do then is take the slow tendency out of the fast tendency here. So probably the slowest tendency I see here is that the second half is a bit lower than this half. So I would probably say there seems to be a low frequency signal which does something like this. And then what I could do is I could take this signal and subtract it from the top signal, one by one, each sample subtracted from the corresponding sample on top. And what I would get is a very similar signal in its detail, but this long-term tendency wouldn't be as pronounced, and I won't attempt to draw it. But what I will attempt to draw is what I might consider the next spectral component, which seems to be that there is this frequency. This goes down, up again, down again. It doesn't really go up, but there seems to be a lot of energy at a frequency something like this. Okay, and then I could go further and say, well, where do I see even higher frequency undulations? Well, I kind of put the dots there and it seems like it, but actually it was a bit like that as well. So there seems to be something of this frequency kind of popping in and out. In fact, every time I have a little corner here, that's definitely full of higher frequency, so I can kind of get some higher frequency signal drawn here as well. Okay, so that's essentially what's going on. We're taking a complex signal and separating it into different components. Now, the main thing I believe you can imagine in terms of how on earth do we do this is, anyone? Jump in. Filtering. Okay, so we know that if we put a filter in the path of that top signal, and in fact if I put 3 filters, well, shall I go into the detail? Let's say I put a crossover filter with 3 bands in the path of that signal, I will get the 3 bottom signals coming out. Okay, so filters can do this. The nice thing is, the interesting thing is that FFT is not a filter bank. So there is something else going on, which is even more mysterious. I mean, filter in itself is quite mysterious, I would consider. Especially because FFT kind of works on a windowed data, so it has a buffer filled with the signal. So you can kind of imagine ways of doing stuff, let's say. But the filter typically, like a second order crossover filter, actually has only 2 previous samples stored, which means that the only thing it sees is 3 consecutive samples. And the real mind-boggling thing is, how can that algorithm, which sees only 3 consecutive samples, separate out this really low frequency? And it can. So really mind-boggling stuff. And I believe somewhere on my YouTube channel there is an explanation about how on earth filter does this, if you're interested. Okay, so how does the FFT does it? Woo, that was a bad sentence. The FFT does it, I'm going to jump to that slide and show it in a second before we get into more detail, is using what I call an amplitude modulation trick. Let me just, actually it's towards the end of my slideshow for some reason, but I feel like we are ready for the punchline, and this is the punchline, except it was somewhere, I just missed it. Let's just give me a second, although I might just be, yes, that's the slide. Okay, so what happens, first, actually even before I show you the slide, I will explain you what happens with amplitude modulation. In fact, I should probably call it ring modulation, or in fact, I should probably call it multiplication. So the thing to start from is to understand what happens when I multiply one signal with another signal. And I'll take the simplest, most example. I will multiply a sine wave with an envelope. Okay, so this is something you've probably seen before, amplitude envelope. The way you do this is you have a bipolar signal which is your audio signal, goes between +1 and -1 in the digital domain. And you have your unipolar envelope, which goes from 0 to 1. If you multiply each sample, each corresponding sample, you will get a signal which looks like this. Well, I'm probably going to do it slightly higher frequency because otherwise it wouldn't show. And this will be your enveloped sine wave. So in essence, what you've done there is applied an amplitude envelope. That's straightforward. Okay? Now the interesting thing is, what happens if I multiply a sine wave with another sine wave? Now the simple case here is that the other sine wave is really low frequency. Okay? In which case it does look a bit like an amplitude envelope, and you kind of get the gist. That's what you get. Now the funny things start to happen when these sine waves become slightly closer in frequency. So let's take a very special case where we are multiplying a sine wave with another sine wave of the exact same frequency. Okay, so that's a nice case study because there's some regularity that we can use in order to come to certain conclusions. So first of all, they're same frequency, same phase, which means that actually what I'm doing is I'm squaring the sine wave. Okay, so multiplying it with itself. What will I have as a result? Well, as a result of this, what I will have that when I multiply two zeros, I get a 0. Clear? Clear. When I multiply two ones, I get a 2. Right? Come on, guys. Someone tell me I'm stupid. What is 1 times 1?
0.
Yes. Great. Let's have a drink. Oh, you have one already. Good for you. So 1 times 1 is 1. Okay, so when I multiply ones, I get 1. Again, I multiply zeros, I get 0. Now, -1 times -1. What's -1 times -1? It's a positive one. It's a +1. So actually, this bottom here will come straight up. And if I do this, obviously it's a cyclic thing, I will actually get, well, I'm kind of off line here. This is supposed to be the 0 here. This is supposed to be, again, the +1. Another 0, another +1, another 0, another +1. Okay? So these are the extreme values. And then, in order to fill in the rest, I can take 0.5. What happens if I multiply it with itself? Square of 0.5 is? It's the half of half. It's the 0.25. So actually, everything in between these extreme points will be slightly pulled down towards the 0 line. Because every decimal number between 0 and 1 squared is slightly smaller than the decimal number that I've just squared. Okay? So it kind of comes down from having a hump up, it kind of starts to have this hump down, a negative hump. What is it? No, a bulge is also humping up. It's a trough. It becomes more like a trough. But actually, close to 1, it's still like this. And I won't go into all the detail here, but straight to the punchline, which is that this is an exact sine wave of twice the frequency. So the funny thing is that the way they multiply together will yield this exact crucial shape of a sine wave. So remember I saying, you know, as soon as you have one little anomaly in the shape of a sine wave, it's not a sine wave and it has harmonics. If you multiply two pure sine waves of the same frequency, you get the double frequency sine wave as pure as you can imagine. The other thing that you get is DC offset. Okay, so you might have heard this term before. It signifies a constant voltage in an electronic circuit, and it signifies a fixed number in a digital audio system. Visually, it is the offset of the center point. Okay, so I did get a clean sine wave from multiplying two of the exact same frequency, but they are also, the sine wave is not centered around 0 anymore. It has DC offset. Okay? Now, this whole thing, from another perspective, is your ring modulator, because ring modulation is essentially multiplying stuff with sine waves. And if you look at ring modulation, the coolest thing is that if I multiply, let's say, 100 hertz sine wave with a 120 hertz sine wave, what I will get, so I'm kind of multiplying the two together, what I will get is a 20 hertz sine wave and a 220 hertz sine wave. And the original two sine waves will disappear. Fact of math. There is an equation, if you look it up, every addition, because you see, if I have two sine waves, it is an implicit addition. They are present at the same time, they are mixed together. So addition of two sine waves actually always equals the multiplication of another two sine waves. So actually this whole story about creating every possible signal by adding sine waves, you can pretty much, although this is something to be verified by engineers of signal processing, my hint is that you can also do the same with the multiplying sine waves. But it's really not relevant. What is relevant here is that we get what we call sidebands. Okay? And what we have, if this is frequency A and this is frequency B, if I multiply the two, what I will get is, well, in this case, B minus A, to keep it simple, and B plus A. So what I get is sidebands, and I have a different sideband and I have a sum sideband. Okay, so multiplying two sine waves of fixed frequency, which means that it's a sine wave, right? So multiplying two sine waves gives you another two sine waves at different frequencies. This is what happens. So actually, if you think about this in relation to the previous bit, where I said that if I square a sine wave, I will get a sine wave twice the frequency. Well, sine wave twice the frequency makes sense because that's B plus A. They were of the same frequency, so it's 2A. So it is double the frequency. And actually, the other bit, that I get DC offset, also makes sense because that is A minus A, that is 0. And DC offset is 0 hertz frequency. Okay? So this is the foundation necessary to get a grasp on how FFT does the magic of separating out spectral components. And how does it do it? Well, I'll show the slide, although I'm not sure I might want to draw as well. But in any case, the way it does it is, you see, I have a complex signal. And if it does not have 0 hertz energy, it is centered around 0, it has no DC offset. This is my starting signal. I multiply this signal with the sine wave. What do I get? Well, for every frequency which is not the frequency of the sine wave I multiply with, all of the other frequencies will get sidebands, some and different sidebands, but all of them will be non-zero. And the only frequency that will deliver 0 hertz energy is the exact frequency that I'm multiplying with. So you see, if I do this, and the way you can imagine this sideband business is that if I have a complex spectrum, let's say it looks like this, right? If I multiply it with a sine wave, then what I'm doing is I'm creating sidebands. In fact, I'm duplicating the spectrum, and one goes lower and the other one goes higher. So I'm kind of doubling it and pulling it away from itself. That's what happens to a spectrum when you multiply with a sine wave. That's your ring modulator. Now, the point is that if I multiply with a single sine wave, I have a complex spectrum. Let's see if I can do this. I have a complex spectrum. I multiply it with a single sine wave. This spectrum will get pulled out of itself, so to speak. And all of the components will be non-zero hertz except the one that corresponds to that frequency. That's the only one that will give me a 0 hertz energy. Which means that if I've started from a signal which did not have 0 hertz energy, which means it was centered around 0, I multiply it with a sine wave, and I look at where is it centered around, right? If it is not centered around 0 anymore, it means that it suddenly has 0 hertz energy, which means that that amount of 0 hertz energy corresponds to the amount of energy at that frequency in the original signal. So by multiplying with the sine wave, essentially what I do is I shift the energy at that frequency down to 0 hertz. And it's really easy to grab it at 0 hertz because it's just the average of the signal, pretty much. It's where it's centered around. Okay? So it's not filtering, right? It is this funny multiplication trick that gives me a DC offset energy and thereby allows me to just grab it, see how much of it was there in the first place. Okay? So that's Fourier. Now, just briefly, now that we're deep in the mud, cognitive mud, things like wavelet transform have a radically different thing, and it's a kind of a tree structure with downsampling at each step, separating the signals and blah, blah. I mean, I'm not a signal processing engineer, right? I love it, and part of the reason I really love it is because it lends itself to these amazing analogies and metaphors and the sense of I understand the world around me or the sounds around me and such, the digital processes around me. But it's deep, guys. Signal processing engineers, I mean, I'm in love with them by default. Okay, so that's actually the big punchline for today. Okay, that there is this trick with multiplication. That's how it does it, and then the things that go along with it, or the things that are also interesting, have to do with how this is performed. Okay, so probably the most interesting thing is this trade-off between frequency and time. Not sure which slide to show here. Probably reading as I speak about different things anyway. So I'll just forget it. The interesting thing is that time and frequency are not distinct phenomena. Okay? Being advanced monkeys, you know, just a sec. We have a very obvious reason to believe that time and frequency are separate, distinct phenomena, because the frequency I hear here and the time is here or on the phones these days. It's just a totally different domain. Nevertheless, they are not distinct phenomena. They're tightly interrelated. Okay, so without time, there would be no frequency. I mean, it's a kind of a really stretched argument. I typically discard this type of stretched analogy or whatever that is. But the point is that a sound is a vibration, and low frequency sound is slow vibration. So for a slow vibration, it is probably easy to understand that for it to exist, it needs time for it to be a slow vibration. Okay? So what you could say is that if I had only 10 milliseconds of time, which is 1/100th of a second, then I would never be able to have a frequency which is lower than 100 hertz. So there is this tight relationship between the two, and it actually goes quite deep into physics, because there is a very similar issue, believe it or not, with velocity and position. It's the so-called Heisenberg's doesn't come to mind. Mr. Heisenberg came up with this, and the point is that this is kind of a particle physics domain. If you measure the velocity of a particle very accurately, you cannot measure its position as accurately, and vice versa. And we have a very similar thing in audio, that if I measure the frequency quite accurately, I cannot measure the time, the onset, quite accurately. Okay, so there is this trade-off in frequency resolution and time resolution, which is really interesting and puzzling. There are tricks to increase, as I learned, the resolvability of a spectrum, but the resolution is fixed. I won't go into these terms. I probably don't understand it fully myself either. But the point is that what you do with spectral analysis, in order to observe a low frequency, you need a lot of time. Okay? Because if you take a short slice of time, the thing hasn't gone up and down yet, so there is no way of you observing whether there is anything going up and down at that frequency. Okay? So the window you take, the amount of samples you take, will determine the lowest frequency you can observe, and the lowest frequency you observe is actually related to the exact length of your window, which is how we call this frame. In fact, the signal, the sine wave that fits a single period exactly into your window will be the lowest frequency that you can distinguish. But if I take a really large window, let's think numbers, I want to go down to 20 hertz. Okay, so it means that I would have to take 50 millisecond window. Okay, how many samples is that in digital audio? Well, it is a 20th of a second, and if we're working at 44K, the 20th of that is 2,250 samples. So if I take about 2,000 samples, right, in order to see the lower frequencies in the signal, I will observe those frequencies, but what I won't observe is the onset time, because what I'm looking at is the whole frame. So I don't know when things happen within that frame. So you see, by increasing the frequency resolution, indeed lowering the lowest frequency that I can observe, I am losing the time resolution. I'm losing the accuracy of being able to specify when something happens within that window. And a 20th of a second Well, you can hear the difference. I mean, it's a kind of a flam. What is the 20th of a second? It's a fairly flammy sound. You wouldn't quite hear it as a, you know, kind of a rhythmical duration, more like a flam like that. But you can imagine that this is just rather inaccurate in certain scenarios. Okay, so that is your resolution trade-off of spectral analysis. And there are ways around this. You can actually take shorter windows for higher frequencies, longer windows for long frequencies. You can take different types of spectral analysis algorithms. You can do zero padding, increase the resolvability, and all the rest of that. But that is actually quite crucial in terms of, you know, practical uses when you get to specify the window size. Now, I've mentioned briefly that fast Fourier transform is the accelerated spectral analyzer that is ubiquitous. And the case with that is, you've probably seen this already, it allows you to only select window sizes which are exponents of 2. So you get window sizes like 512, 1024, 2048, 4096, and so on. 8192. It's beautiful how these things, you know, just almost dream with those numbers by now. And that has to do with the structure of the algorithm, this tree-type structure. And if it has a number of samples to deal with, which is an exponent of 2, then it exactly fits into this tree structure. But actually, the Fourier transform itself, without the acceleration, what it would do then, as I explained how it works, it would take the fundamental frequency corresponding to this window size, this sine wave, multiply that sine wave with this signal, and check the resulting DC offset. Then it would take the next frequency that fits into this window, which is double that frequency, twice up and down, multiply this signal with that sine wave, check the DC offset, and note the energy at that frequency, and then it takes the next one up. Because the funny thing to realize is that the frequency, I should say the pitch, but actually frequency is a good term here as well. The frequency of a signal does not directly relate to, as I said, the constant angular frequency. It actually relates to the rate of repetition. Okay, the sine wave is all about constant angular frequency, but signals in general are about repetition rates. So the funny thing to realize is that if I have a signal which is a sine wave of a given period, right? So this is a time duration, 1 over that time will be the frequency. And on the other side, I have a signal which is derived from a higher frequency sine wave, but it is zeroed out for the rest of its duration. This signal. These two signals have the exact same frequency. You hear them having the exact same pitch. Okay, so this means that it's not the shape of the sine wave that gives me the frequency, the pitch. It is the rate of repetition. Which actually means that whatever I do, and literally whatever, I can take white noise. You might be aware that this is a set of totally random samples between -1 and +1. If I take pure white noise, but repeat it at a rate which corresponds to an audible frequency, let's say 10 milliseconds, I repeat this exact same thing, I will not hear white noise. I mean, I will hear a pitched white noise. I will hear the pitch of this signal. So whatever I do in 10 milliseconds, well, it's not too much time to do anything really. But whatever I do, if I repeat that thing, what I will get is a fixed pitch signal. And even more importantly, all the components of that signal will be harmonics of the fundamental. So whatever I do, if it is being repeated, so how do I know that? Times 2 times 3. So I'm repeating the exact same waveform. No matter what the waveform is, if I repeat it, the only thing it will contain is exact harmonics at different levels. It cannot contain a frequency which does not exactly fit into the window. You see, and that has to do with what I've just said. If I have this signal, the frequency, if I repeat this waveform, the frequency will not match the sine wave that is squeezed down there, but it will actually be the duration of the period, the repetition rate. So actually this signal also contains strictly harmonic spectral components. So actually, and this is quite interesting because we are still kind of living in the, you know, we think the way people thought about sound 100 years ago, unfortunately still, which is, oh, if you have the waveform of the instrument, you know everything about it. No, not at all. Okay, so the detail of the sound, the quality, all the things we love about the sound have to do with the fact that the spectra are constantly changing. By repeating a single waveform, you get a buzz. No matter how beautiful that waveform is, no matter whether you've derived it, you know, with an elaborate conceptual, socially whatever scheme, it's just a buzz. Okay? So in the same fashion, if I do FFT as a matter of spectral analysis, what I'm able to get at is only the fundamental frequency which relates to the window length and its exact integer multiples, its harmonics. I cannot get an estimation of anything in between these things. Which actually means, because this is, so let's take an example. If this is a 20 hertz fundamental, then this is 40, 60, 80, 100, 120, so forth. Now, if we look at the musical interval corresponding to these pairs of frequencies, at the bottom this is an octave, right? 20 to 40 hertz is a full octave. 120 to 140 hertz is it close to a semitone? Probably not yet, but it's about a second interval. So actually, musically, or in the way we hear things, what we have is that we have really low resolution in bass and really high resolution in the high frequencies. Because these frequencies are spaced linearly, and our hearing is more akin to a logarithmic scale. Okay, so that's this other issue with FFT, this resolution. We have a resolution trade-off with the time, but we also have low resolution for low frequencies and much better resolution for high frequencies. Okay, so these are just facts of life in terms of an FFT. Okay, there's a few more things. I'll kind of jump over these. I think we've probably had as much cathartic realizations as we can in a session, I hope. There's a few more details here. So typically this is, oh no, you're not seeing it here. So what you have then is a windowed signal, which means that if you have, you know, a longer signal, you have multiple frames like that. The thing that you do typically is you do some kind of overlapping. I won't go into this. Samples, we just discussed the trade-offs. And here is the windowing. So there's few more short bits I just share about windowing, because it's one of those things that you might encounter when you specify parameters of your spectral analyzer. The point is that the shape of the window determines the shape of the skirt. If you remember what the skirt was. So the thing is that if you put a sine wave into a frequency analyzer in real life, you will not have a single bar. You will have a slightly wider thing. You will have a skirt. And then the shape of the window is determining this. So I said something about the Gaussian shape coming back. But in essence, what you have is that the sharper the window, the broader the spectral anomalies, so to speak. And there's quite some detail on that. I mean, technically, you don't really worry about that much. Here is a bit about overlapping. Okay, so how would the overlapping help my resolution trade-off problem? Let's see if anyone has thoroughly understood everything I just shared. So if I introduce overlapping, how does this change my time frequency resolution trade-off problem? Well, what happens is that if my window size is the same, then my frequency resolution is the same, right? Because these are tightly related. But if I start to overlap the windows, then what I get is slightly higher time resolution, right? Because I'm increasingly able to pinpoint the moment in time when something happens. And it's not smeared into this large window. I mean, it is kind of smeared into the large window. It's a tricky argument, but there is this fade-in, fade-out business, and the window itself. But I do get slightly better time resolution. Again, if you talk to a signal processing engineer, he will show you an equation, that's what happened to me, and explain you that the resolution does not change. And then if you really insist, like I did, and came up with examples, then he will come back and say, well, you increase the resolvability of components, but not the resolution. There you go. It's a bit like, you're just too far away from comfort zone to be able to argue anything at that stage. Okay, and then probably the last thing to share is something about the phase. Okay, so technically, if we look at this, I mean, technically the phase itself, in fact, I could probably do another hour on phase alone, but I will spare you from that. The interesting thing about phase is that when you learn about it, it seems really simple, but then likely very soon you realize that something's fishy. So the thing about the phase is that zero phase means that the signal, the sine wave starts at zero with zero phase. That's a horrible description. But the way you kind of get to understand the phase is that there is a time delay. So if the phase is different between two sine waves, it means that they're not aligned, such that peak corresponds to the peak, but there is a kind of a time delay between them. Obviously, if these are sine waves, then there is no silence here. It's just that it might look a bit like this. And you've probably seen this one when you have two sine waves exactly out of phase, which means that every peak corresponds to a trough. If you add them up, you get pure silence. Okay, so that's your destructive interference. So technically what happens is that when I analyze my complex signal, okay, and then my analysis says that at the fundamental frequency corresponding to this window, there is energy of this amount. It will also report the phase of this signal, which is just the value at that frequency bin. So for a spectral analysis, what we get is a magnitude spectrum, and we get the phase spectrum as well. So how does this happen? Well, I've introduced the rock bottom of it in terms of explaining what happens with sidebands when you multiply with sine waves. So it's probably worth just connecting the dots here. How do you get the phase? Well, actually, you don't multiply with a single sine wave. You multiply once with a sine wave and once with a cosine wave, which are 90 degrees out of phase. And then from those two, you can derive the magnitude and the phase. You see, because if I only multiply with a single sine wave, but the signal has that frequency in opposite phase, then I will never see it, more or less. But in any case, the amplitude will not be estimated well. So actually, for each spectral bin, I have to multiply twice, once with a sine wave, once with a cosine wave. And then you get the thing that you might encounter if you play with FFTs, maybe in max MSP or anywhere else. The fact that what you get is real and imaginary, x and y, sine and cosine. But actually what you're after is the magnitude and the phase. Okay? So this is how this actually works. So if you get raw FFT data in max MSP, for example, okay, what you will get is a real and imaginary component for each bin, for each frequency. And then you would have to convert from Cartesian to polar to get to the magnitude and the phase. Because if I just multiply with the sine wave, gives me this, just with the cosine gives me this, but none of those is the actual magnitude of your spectral component. So that's your thing there. But the interesting thing about this phase business is that you see, it's really tricky thing to understand. I mean, if you just come to the question of it, that's great already. But you see, if I've shown you how what I'm actually doing is I'm looking at the energy at 100 hertz, looking at the energy at 200 hertz. But because it is an orthogonal transform, right, it will yield the exact same original signal. If I put a 150 hertz signal through this spectral analyzer and I resynthesize, I will get the 150 hertz back. So how does that happen? Right, so I have information at 100, information at 200, but it encodes 150 as well. And the way that happens is through the information that resides in the phase. Because the phase, you see, if my phase signal, if my phase is progressively incrementing, growing, becoming larger, then what I'm actually doing, I'm stretching the signal. So I'm getting a lower frequency. Right? Because you see, if in one window I have 0 phase, and then in the next window I have, I don't know, 20 degrees, if I express it like that, it's moved away. So it's coming later. And then the next frame I get 40 degrees, next frame I get 60 degrees. I am progressively stretching the signal, so actually I am able to encode something at 150 hertz. Which means that not all of the FFT goodies are in the magnitude spectrum. In fact, if you do this, I'll probably skip doing it at this stage, but if I take this raw FFT, do the polar conversion, do the inverse FFT, I would get the same original signal back. But then what I can do is I can make the magnitudes all flat. So this whole beautiful shape that describes the spectrum, the magnitude spectrum, I can fix all of these values to 0.5, and I will still recognize the signal. I will understand it if it was a speech, maybe even recognize an instrument if it was that. Because there's huge amount of information in the phase, in the ways that these given fixed frequencies move about frame to frame. This encodes also quite a lot of frequency content. And phase is really bad because actually it comes wrapped. So if you look at the phase signal, do I have one here? This is typically the phase signal. I mean, this one is actually looking quite nice, but you have this periodic wrapping going on, and you have to unwrap the phase, and things get really complex and all of that. Okay, there's quite a few more things I could talk about. Maybe just one last thing, and then it's questions times, of which there will be none. The one last interesting thing, so you understand that if I do an FFT, I get a spectrum, magnitude, and phase. If I do the inverse FFT, I get the time signal back. That's straightforward. So both of these are complex tree structure algorithms that it's just futile to even start trying to understand. Now, the interesting thing is that what we have as a matter of spectral analysis, which builds on this, is what we unfortunately call phase vocoding. And it's unfortunate because, you know, there's plugins and things and prejudices, so it means many things aside of its technical significance, which is that from a set of fixed bins, so bin is the term for a frequency in spectral analysis. So from having a set of fixed frequencies, and for each of those frequencies having an amplitude and phase trajectory, instead, from this data we can derive variable frequency content, data structure, right? Such that, for example, if there was a 150 hertz sine wave in the original signal, it won't be some magnitude and some phase at 100 and some magnitude and some phase at 200, and those combined will yield 150, but instead I will have a 150 hertz trace. And once you get to this phase vocoding analysis, you will start seeing that in time there are trajectories. It can actually trace frequencies going up and down in time. Okay, so this is not raw FFT, it is something more on top. From a raw FFT you get what we call a spectrogram. So you get these typically colorful plots whereby time is horizontal, frequency is vertical, and then the amount of energy is colored. So you see how much in the highs, how much in the mids, how much in the lows. But if you get a spectral analyzer like Spear, you can note this if you want to play with this stuff and move bins around and experiment with this. Spear is a free software that does this. Then you will get traces going up and down. And from there, if you want to get the sound, it's not an inverse FFT anymore, it is an oscillator bank. Because you have actually reduced the signal to traces of frequency and amplitude rather than amplitude and phase. Okay? So that's your next step, and there's millions of things that build on FFT and all the rest. But yeah, I don't know what do you guys think? Was this a worthwhile? I see some of you are really having it, and I see some of you are really not having it as well. But that's what I've expected, so I hope it wasn't horrible. And thank you for your attention. If there is any questions, I'm happy to elaborate. Yes?
So, talking about sine wave, depending on how long sine wave is
Yeah?
affecting like the skirt.
Yes.
Is that a physical thing, or is that just a psychoacoustic?
It's physics, it's mathematics.
Okay.
It's trigonometry.
Yeah.
Yeah. I mean, in physics, you know, I mean, these things are quite tricky actually, because the thing that I said about how should I put this? I mean, I don't want to open a can of worms. In fact, I do want to open a can of worms, but I just want to do it gently, such that they don't all come out and eat us. The funny thing is that if I have two spectral components of 100 hertz and 100.5 hertz, I will not hear two sine waves, right? I will hear a beating. I will hear a period of 2 hertz and one frequency going up and down in amplitude. Okay? And at some point, if I space these sine waves apart, I will stop hearing. Well, first, the amplitude modulation will start to speed up. And then it will get a kind of a gritty character. And then I will suddenly hear two frequencies. And this is psychoacoustics, because it has to do with my ability to resolve these things. And the same phenomenon appears with 3 different phases. One is amplitude modulation. The second one is a kind of a textural character, if I may. And the third one is multiple frequencies. In physics, it's the exact same thing, right? And that's the funny thing, because actually, you see, when I said that I can express the same thing by adding 2 sine waves or multiplying 2 different sine waves, it's that same thing. Because if I have this 100 and 105 hertz, I could achieve it by adding those 2 sine waves, but I can take one sine wave and apply a half hertz modulation on it. So from physics point of view, those are 2 aspects of the same thing, which is mind-boggling, especially because psychoacoustically these are 3 different phenomena depending on the distance of the sine waves. So it's beautiful. Okay, so this skirt, I don't know if it really relates to this, the way what you were interested in, but yes, this skirt is also something which is a trigonometric fact, that if it's not an infinite sine wave, the spectrum is just like that. But in terms of how we perceive it, the psychoacoustic side is complex on top of that mind-boggling duality. All right? Cool. Anything else? Great. Well, thanks for being here, guys, and enjoy the afternoon.